So it is my great pleasure to introduce Kedar Namjoshi from Bell Labs. So he will give the invited talk in our workshop. I mean, Kedar in general had a very large number of influential works on model checking, especially related to compositionality and symmetry reductions. And more recently, he is interested in like proving the correctness of various kinds of program transformations. And his talk today will be about one particular program transformation, which are some class of program transformations which are used in compilers. So please, Kedar.
So I'm going to go to full screen if this actually works. Then okay. So let me hang on. I'm just trying to. Okay. All right. So thanks, Konstantin and Andre, for inviting me to give the presentation. It's great to be here. So before I start, I just want to say that we've just been discussing about how life is in this online world where you're barraged with online meetings, online calls, online lectures to give, online talks to attend, and it's really easy to sort of lose the thread of what is happening in a talk. So my solution for that is to ask questions, and but now I'm on the other side. So what I hope you will do is interrupt me. So please interrupt me. Please ask questions, or if you have comments or thoughts about what's being presented, I would definitely welcome this. So I'm in no rush to get through the slides. So just so you know, there's about 30 or 35 slides in this talk. So with that, let me begin. So we're going to talk about designing a self-certifying compiler. Now, maybe the only word that is unfamiliar in this is self-certifying. So I'm just going to go right into a little guide to self-certification. So it actually turns out it's a very general idea that doesn't have, it happens to have application to compiling, but it also has application to many other things. And so it's something that you might carry away from this talk and apply it to something else that you're doing, not necessarily, program equivalence or compiling. So let me tell you what this is about. To begin with, I'm just going to start by thinking about the verification problem in this way. So you're given some kind of mathematical function from x to y that you want to compute, and you've written a program P that translates inputs in x to outputs in y. And now the question is, does program P actually implement the function f? Right? And so this is a classic verification problem. It's not a new problem. So just for some fun, this is a quote from, I would say, a very well-known computer scientist. And it's a very old quote. You can tell that by, I just did cut and paste, and you can tell that it's been typewritten. So that should give you some idea of how old this is. So just to read it out, it says, to put it quite bluntly, as long as there were no machines, programming was no problem at all. When we had a few weak computers, programming became a mild problem. And now that we have gigantic computers, programming has become an equally gigantic problem. So I'm going to give you, unfortunately, I don't have you right in front of me as an audience. So I can't ask for, guesses as to who this is. But if you have a guess, put it on Slido. But let me go ahead, give you a couple of seconds to think about who this might be. And then I'm going to reveal who it is. Okay. So this is a quote from Edgar Dijkstra. This is from his Turing Award lecture, The Humble Programmer. It's a fantastic lecture. It's something I recommend everyone reads and maybe rereads every few years, just to see how ahead of his time in some sense he was. So I happen to have the really good fortune to get to know Dijkstra as a grad student. So he was at UT Austin, where I did my PhD. And this is how I remember him sitting in his office with a slightly quizzical expression on his face. And uh, I would always think of myself as the mouse and Dijkstra as the cat. And so he was, his expression said that, I know you're going to make a mistake in the next few minutes and I'm ready to pounce. But he was actually a very nice person once you got to know him well. So he had a fearsome reputation, but he is a very nice person. So, and like I said, he was right about a number of things. And so let's go to what one would do classically about the verification problem. So you're interested in knowing whether program P implements F. And maybe the simplest and perhaps the oldest way of getting some confidence in the answer is to test. So you generate many inputs from X and check for each input whether the output of the program equals the output that you expect or the result that you expect from the function. And of course, this only works if you can calculate the result of the function easily enough. And sometimes that's not always the case. So and of course, as Dijkstra pointed out many years ago, testing can show the presence of bugs, but not their absence. So to prove that your program is actually correct, the classical approach is to try to establish this as a theorem. So you want to say, for all inputs, the output of the program on input X equals the result of the function on input X. Now, this is basically the business of CAV, and this is what we've been working on for many years, and in fact, many decades. So there's been, of course, considerable improvement. There's lots and lots of theoretical techniques that tell you how to establish such a theorem to do program verification, in effect. And many of them have been implemented in proof assistance and in model checkers. And there's this whole decades worth of work on trying to basically establish theorems like this. And I would say it's been really successful in targeted domains, but it's still a huge challenge to apply it to many other kinds of programs. And so one class of programs for which this is a huge challenge is compiling, and we'll get to that in a minute. But what I wanted to get to was an idea called result checking, which is somewhere in between testing and full verification, if you like. And so this goes back, or it was really, I think many people have come up with this idea, but it was really well expressed in a paper by Bloom and Cunnan in 1989. This is a JSCM paper that we should maybe take a look at some point. And the idea they had was that given the function f, you design a checker for it. And what the checker does is that it takes, let me see if I can turn on the laser pointer. Okay. So the checker takes the input x and output y. So it basically takes a value from x and a value from y, and then tells you whether those two are consistent with each other. It's either true or false. And the property that you want from the checker is this soundness property that says if you give it x and y and the checker says yes, then it's true that the value of the function on x equals y. Okay. Now in a real application, what you also want is completeness. That is, you want the direction of the implication to also be reversed. But we're just going to stick with soundness for the time being. And actually, what Bloom and Cunnan do in their paper is that they design checkers that are probabilistically sound and probabilistically complete. So I'm not going to talk about that, but it's a really interesting direction. So now, once you have this checker, what you do is that every time you run the program on an input A and obtain an output B, you pass the pair A-B to the checker. And because of this property, if the checker says that pair is okay, then you know that the output of function f on input A is actually B. Okay. In compiler verification, this is called translation validation, and it actually predates Bloom and Cunnan's work. It goes back to a thesis of Hanan Samet in 1976, and it was, in some sense, lost for a while, and then independently rediscovered about 20 years later by Pinelli, Sigel, and Singapore. So I just want to make a couple of observations about this checking idea, which is that what it does is that it basically takes the program out of the picture. So the checker is something that only depends on the function that you're trying to compute. So it has nothing to do with the program that you actually use to compute the function. Right? So what that means is that the correctness of the program is no longer something that you need to worry about. You do need to worry about the correctness of the checker. It has to have this property. But typically, and you'll see this for compiling, it turns out that the checkers are actually simple to implement, and actually much smaller than the compilers that they are checking. So like orders of magnitude smaller than the compilers that they're checking. So there is actually hope. So first of all, it's you can do code inspection on these checkers and make sure that they're actually okay, and gain some confidence. But you can also do, in principle, you can also do these mechanized proofs to make sure that your checker is doing the right thing. So let me pause for a while and see if people have any questions about this. Okay. So let's look at something that's closer to CAV. How would you check a SAT solver? Now, in its most basic form, a SAT solver is just a function that takes Boolean propositions and returns either SAT or unsat. Right? But okay, so now let's try to figure out how to design a checker for it. So you run this program that this complex SAT solver that you have, and it gives you a SAT. How would you know that this is actually correct? Right? So you're given the input phi and you're given the output SAT. Now it seems that we are stuck, because in order to figure out whether this answer is correct, the checker would have to, resolve the Boolean satisfiability problem, right? And that's something that we don't want it to do. So the way around it is to generate more information out of the SAT solver. So you want the solver to take a proposition, give you back the result, either SAT or unsat, but also give you this extra information that in some sense you can think of as certifying the result or justifying the result. And now the checker is similarly extended. So it gets a proposition as input, it gets this extra justification for the result. And now with the help of this justification, it's easy, or much easier, as you'll see, to decide whether the result is actually correct. So we're going to call this extra information either a certificate or a witness or a justification. These are all helpful names for this additional information that it produces. But they sort of give you a sense of what it is for. And once you have, and I'll just call it a certificate from now on. So now checking turns out to be easy, right? Because if you have a SAT answer, then what you want to do is to produce a witness that is, or a certificate that is an assignment of Boolean values to the variables of the formula. And this is what we call a satisfying assignment. It's very easy to evaluate the formula under that satisfying assignment and decide whether it's true, right? So the checking process is really the evaluation of the assignment that is generated. What would you do if the solver returns unsat? What kind of witness would it produce, or could it produce? And one possibility is that it could actually produce a proof of the validity of the negation of phi in a standard proof system. So if phi is unsatisfiable, then its negation must be valid. And so there are many proof systems, step-by-step proof systems for propositional logic. You can produce a proof in any one of those systems. And now the checking becomes proof checking. So you're basically making sure that every inference that is made in the proof system, every step of inference is correct. And because of the soundness of the proof system, you know that if it eventually says that if every step is correct and it proves the validity of not phi in the final step, then that answer is actually correct. So what we have done here is we have created this, we have sort of designed this extra information that would make checking easy. But now the person who's writing the solver has to do a little more work. They have to not just return the answer, but they also have to produce this witness. So we're making the programmer, in some sense, help us verify their own program. And so this is why I call it self-certifying. It's basically the program that you run produces by itself as a candidate certificate of its own correctness. And now it's up to the checker to decide whether that certificate is correct. So this little purple square is telling me that it's this is where I want to pause to see if people have questions or thoughts on what is being said so far, and if there are doubts about what self-certification actually means. Okay, I guess if you do, then send in a question on or comment on Slido, and I guess we'll Constantine or Andre will repeat it back to me. So. Okay, all right. So now so I'm assuming that everything's clear so far. So remember what self-certification means is that the programmer of the solver has to do more work to produce the witness. But what that does, the witness actually makes it very easy to write a simple checker that certifies that the answer is correct. And because the checker is actually independent of the program doing the solving, you can write a checker once and then use it to validate a number of satisfiability solvers. And now the code of the solvers can be as complicated as you like. You can throw in heuristics, you can take out heuristics, you can do all sorts of special cases in the SAT solver. And these are the kinds of things that make full program verification really, really difficult to do. And so now you don't have to worry about any of that or the correctness of any of that, because all of the results are getting checked. And the only thing you have to worry about is the correctness of the checking algorithm, which, as you've said, is actually quite simple. So that's actually a very liberating way of programming. So you're programming as before. You're of course programming carefully, but you don't have to write a formal proof of correctness for your program. Okay. Now that's for SAT solvers, but you can also do the same thing for model checkers. So a model checking program is a function that takes a program and a property and tells you whether the property is satisfied or it's unsatisfied. Now, a self-certifying model checker would actually produce something more as information, would produce a witness. And what would that be? So if the property is satisfied, you can actually generate a deductive correctness proof from the model checker. So you can figure out what the invariant assertion should be. You can figure out what the rank function should be in order to prove the correctness of the property. And this gets a little more complex if your property is a temporal property. So you have to do the invariance and rank functions with respect to the automaton for the property, but it can be done. Unsat is the case we are all familiar with, where the model checker doesn't just say that it's not satisfiable. It says that it's not satisfiable, and here's a counterexample. And once you have the counterexample, it's easy to simulate it on the program and make sure that it's actually a real counterexample and get some idea of why the property fails. So the interesting case was the SAT case. I mean, the unsat, the counterexamples model checkers have been producing since almost the beginning of model checking. And for the SAT case, I wrote a paper at CAV. It was almost 20 shocking years ago. And it turns out that Amir Pinali, Doron Pellet, and Lenore Zook also wrote a paper at the same year about the same problem and with a very similar idea. So this was somehow in the air. So, and these kinds of coincidences do happen. What makes this an even like a strange coincidence for me is that Doron and I were both at Bell Labs. I mean, I still am. Doron was at Bell Labs at the time, and we had offices right next to each other. So we would meet every morning, go for lunch, go for coffee, and somehow we never talked to each other about. We talked about a lot of things. We just didn't talk to each other about this problem that we had been working on until the papers came out. So it's one of the strangest coincidences I've been involved in. Okay, so you can do this for model checkers. You can also do this for graph algorithms. So a test for planarity would just tell you whether the graph is planar or not. If it is a self-certifying test, then it would produce a witness. What would that witness be? Well, if the graph is planar, then you can produce a planar drawing of the graph, which is basically embedding it in a plane where the edges don't cross each other. If it is non-planar, then you can produce what is known as a Kuratowski subgraph. So this is, if you remember from graph theory, there's a beautiful theorem of Casimir Kuratowski from the 1930s that says that a graph is planar if and only if it doesn't contain a subgraph of two specific types, K5 and K33, I think. That theorem is not very useful for detecting planarity, but it's very useful in the direction of showing that a graph is non-planar because you can sort of highlight the Kuratowski subgraph that you have found in the original graph. And so people in graph theory have been working on this. Kurt Melhorn and Naher, I forget his first name, have been working on this since the early 90s, although this is the paper that kind of pulls together all of that work. So one of the things I want you to see is that thinking about self-certification is fun. It's like a puzzle. So if you're computing a function f, you start thinking about, well, what could I do in order to make a good certificate for f? So one that is easy to produce, but also one that is easy to check. Right? And each function would have its own peculiarities with respect to the kind of certificate or witness that you produce. So now I'm actually going in to talk about program transformations, but I hope you've had a good feel for self-certification and that you might actually want to think about how you do it for your own programs, the kinds of things that you write. I assure you it's a lot of fun to think about.
Hi, Kedar. There is a question on Slido.
Mm-hmm. Yeah, I see this. Yeah. So, right.
So the question is, what tools are used to
automate witness generation? I'll come to this question so there are no tools. You really have to think this. So the big answer is that you really have to think this through yourself and, write your algorithm in such a way that it's easy to extract the witness from the algorithm. So you're basically, in terms of compiling, you're writing your compiler in such a way that it's easy to produce the witness. And I'm going to show you a couple of examples of how to do that. And if that doesn't help answer your question, then please come back with it. Okay. So why compilers? Well, this audience doesn't need an introduction, but for one thing, compiling is everywhere. Once you start looking for it, you find it in all sorts of situations. The other thing about giving a talk on compilers is that it's really hard to find pretty pictures. I mean, I envy the people who give talks on machine learning because they can, put up pictures of cute cats and furry animals. And all the best I can do is to put up the dragon book cover. So which actually is a really nice picture. So compilers are everywhere. They're also huge. They're remarkably huge. So here's a website that I found that keeps track of the lines of code in various open source projects. And this is from about a year ago, I think. The snapshot is from a year ago. And this is for GCC. So GCC has about 7.5 million lines of source code. And this is not including blank lines or comment lines. This is actual source code lines. That's an astonishing figure. So it's kind of scary that when you just type these three little letters, GCC, 7.5 million lines of code spring to attention on your behalf. But it's not just GCC. LLVM, which started much later, already has about 2.4 million lines of source code in it. And so there is, really no hope of formally verifying those source code lines. And you have to do, and formally as in a cock proof, you have to do something else. So, and that's something else I'm going to suggest is self-certification. So the way we're going to think about a compiler, so a compiler really has a front end, which is the parsing part that parses, let's say, C and turns it into some intermediate representation. And then it has a large middle end, which is not the right way to put it, but it has sort of a large middle section where most of the optimization happens on the intermediate language. And then it has a often diverse sort of final section, which takes the intermediate language and then turns it into code for specific architectures, and maybe does a little bit of people optimization. So we're going to focus on the middle part, which is where most of the standard optimizations happen. And you can actually think about certification as happening per optimization. So since it's already modular in terms of just running a series of optimizations, you can do certification one optimization at a time. So you imagine this gray box, which is the original optimizer. You add a little piece of code that generates certificates as it runs. And as the optimizer takes program S and generates program T, it also optimizes it to produce program T. It also produces this certificate. So this is the same self-certification idea that we've seen. And now you want to write a certificate checker that takes the input, which is program S, and then a certificate W and the result T, and decide whether the certificate is correct. So the natural questions, and I see a question on Slido about whether there are classes of functions where the witness would be hard to generate. Possibly. I don't know. I mean, I'm guessing the answer is yes, but I don't know of a proof. I'm going to show you some optimizations where towards the end where it actually is hard to produce, to automatically check the certificate that you produce. So hopefully that helps get some insight into this. So really what you want to ask yourself is, what's a certificate? How difficult is it to generate? How difficult is it to check? And how much human effort goes into writing this certificate generator? I'm going to try to give you a feel for these answers to these questions. So first, let's fix what certifying an optimization means. So an optimization that takes you from S to T is correct if the behavior of T is a subset of the behavior of S. And by behavior, I mean input-output traces. Right? So you don't care about the actual code that gets executed. You just care that the input-output behavior of T, every trace that T can generate, that's also a trace of S. And the reason it's a subset rather than equality is because there are some optimizations that actually cut down on, let's say, undesirable behavior of S. So if your program S can divide by 0 and raise an exception, you might want to translate it into a program T which halts before doing the division by 0. Right? So that changes the trace behavior slightly. And now how would you prove language inclusion? Well, there's a very standard technique, which is to use simulation relations. And that's what we're going to call certificates. And these are sometimes also called refinement relations. So a certificate here would just be an inductive relation over the state space of T and S, like a pairwise relation that preserves input-output behavior. So in this cartoon picture here, we have state S and T, which are related. So state S is in the source program, state T is in the target program. They're related by this witness relation. And the inductive behavior that you want is that if T can take a step from state little t to little t prime, then there is a step that the program S can take, the source program can take, from little s to little s prime, so that these two states are again connected by the witness relation. And moreover, what you want is that if during the step you do some input output, then the matching transition from in the source program should also behave in exactly the same way. So that's your inductive reasoning. And you can see just by applying induction that if you now have a long computation in program T, like a long purple computation, you can break it up into steps and match each step with a step of program S, and that gives you a trace of program S, which has the same input output behavior. So the question on Slido is that is it a bisimulation? In many cases, it actually is. So, and like I said, we go with language inclusion because there are, and simulation relations, because there are some optimizations that delete behavior from the source program. But most optimizations that I've looked at are actually equivalences, and they can be handled with bisimulations. So the relation is actually a bisimulation. And you'll see an example in a minute. Yeah, and the question is, are you checking a given relation as a simulation is arbitrarily difficult, is it not? And yes, that is true. And the surprising thing, and the thing that really makes this work for compilers, is that, or the surprising thing to me, was that for almost all of the standard compiler optimizations that you would find in a compiler textbook, for instance, the relations are incredibly simple. They're basically mostly about equalities. And so if you have a relation that's about equalities and you can represent the single step semantics of your programs in an SMT capable form, let's say, then you can use SMT solvers to check the inductiveness property. And that's what we're going to do. So yes, in the worst case, the relation could be really difficult and something that is out of scope for SMT solvers. But in the vast majority of cases, it actually isn't. And that's a very pleasant surprise to have. Okay, so this hopefully also adds on to what I just said, which is that, for all of these optimizations on the left and many more, the certificates are really simple. And so what you're doing in, going back to the self-certification idea is that all of the compiler code, including the certificate generation part, is untrusted. It may have bugs. You don't care. What you do care about is that certificate checker should be sound, so that any bugs that are introduced over here are caught over here, are guaranteed to be caught. That you never certify a program transformation to be correct if it actually has bugs in it. And of course, so the thing that helps you is that the bugs that a compiler has or may have are often corner cases that may not arise in your own source code that you're compiling. So this is a very selfish notion of correctness. You only care about whether the compiler is transforming your program correctly. And if it does so, you're happy. You really don't care whether there are some corner cases that somebody else might run into where the compiler does something wrong. And of course, if the certificate check fails, then there is this question of, how do you go back and find out what the bug was? And the checking could fail for two reasons. One is that the optimization itself is incorrect, so you can't produce a correct certificate. Or it might be because the certificate generator was wrong. And what that means is that the compiler writer did not think carefully enough about all the different cases that might arise and the equivalence proofs that you would need for those. So both of these are useful feedback to give to the compiler writer and have them figure out what it is that was wrong. Was it the optimization or was it the certificate generation? Okay. So now, as seems to be common in this area, the same idea was rediscovered by us. So the original formulation was by Martin Renard and his student Darko Marinov, a student at the time, in 1999. And Lenore and I came up with it independently, 14 years later. So, but it's the same concept. So now I'm going to show you, just walk you through a couple of optimizations to show you what the witnesses look like. So let me take a break and see. Yeah, okay, so a couple of questions. Proving simulation and bisimulation often require an inductive invariant. Is that part of the witness? Yes, it is. So the relation basically, includes any inductive invariant that you need on the individual programs. And the other question was, why is a step related to input output? Well, because so it's not necessary that every step produces IO, but if it does, then we want the input output to be matched on the other side. And I haven't really told you what a step is. Is it one instruction? Is it a block of instructions? Is it like a path through the control flow graph? All of these are perfectly valid ways of defining step. And you could play around with these definitions for each optimization that you look at. Okay. So yeah, so the question is the method is it correct to assume that the method cannot be termination sensitive? We usually need a co-inductive proof otherwise, but I cannot see how an SMT can handle. So I'm not sure what you mean by termination sensitivity, but basically what we are doing is a co-inductive proof. So we are doing a simulation relation or a bisimulation kind of proof. We are generating such a bisimulation relation. And so that takes care of arbitrary length traces. We can by adding maybe more information make sure that if the target program terminates, then the source program also has to terminate. So we can strengthen the relation to make that happen. So you'll maybe see some examples as we go. Okay, so let me do a quick time check. Okay. So here's the relation to the dead store elimination transformation, right? So what's happening on the left is that you just have a straight line piece of code that eventually prints the pair x, y. And it turns out that this statement, the one in red, is useless because x is going to get redefined 2 steps later. Right? So what dead store removal would do is it would just remove this statement and replace it with skip, leaving everything else the same. Now, if you have this program, how would you prove that the behavior on the 2 sides is identical? Okay. So you start off assuming that the values of x and y are identical on the 2 sides. So I'm going to write the values of x and y on the left over here, and the ones of x and y on the right with a prime. Okay, so the prime doesn't mean next state. It just means state in the other program, in the target program. So initially, everything is equal. At this point, you can only assert, after doing these 2 joint transitions, you can only assert that the value of y is the same because the value of x could be different. But that's enough to show that the value of y continues to be the same after the next. And that's enough to ensure that the values of x and y are the same at this point. I hope you can see that. And once the values of x and y are the same, we know that the print statements are going to produce the same output, and the values of x and y continue to be the same after the print statements. So this thing over here is the witness that the compiler must produce. So it should basically say which point in the target program is connected to which point in the source. Right? So that's the control flow graph relation. And it should tell you along this pair of connected points, what is the relation that holds between the values of the variables on the source and the values of variables on the target. And as you can see for this optimization, all you have are equalities. Now, so this was just one example. How do you instrument a compiler to generate such a relation for all programs? And it turns out there's a very simple pattern to the certificate, as some of you may have seen. So you're relating states, always relating states at the same program location. So the arrows are perfectly horizontal. And along each arrow, your horizontal arrow, you're including a term like, y equals y prime, precisely when the variable y is live in the source program. Okay? So the value of y is going to get used in the future. So the value of y is live. The value of x is not going to, at this point, is not going to get used in the future. So it doesn't show up over here. And as it turns out, to do dead store removal, you actually have to do liveness analysis in your program. So all of this information is something that the compiler already has available sitting in some data structure somewhere. And it's the job of the proof generator now, the proof generator code, to just print it out in the correct format. And to check the relation, one has to just do an inductive check. So you assume that y equals y prime. You modify y prime over here, okay, by adding 1 to it. And you modify y over here by adding 1 to it. And then you reestablish that the new values of y is equal to the new value of y prime. So that's the SMT check that you're producing for the SMT solver. And for that, the crucial thing is that you do need the program semantics to be expressible in SMT form. The simple program semantics, single step program semantics, if you like. Okay. Now let me go over a slightly more complex transformation. So this is the SSA transformation. And for people who are not familiar with it, I'll just explain what it does. So the SSA transformation doesn't actually optimize anything. What all it does is that it renames the values of, renames variables so that every variable is assigned to only once, statically, only once in the program. So in this particular program, you can see, for instance, let me just move this out of the way. You can see that, variable x is turned into x0. Variable y is assigned 3 times in this program. And it's actually turned, each assignment is given a new name. So this is y0, that's y1, that's y2. Okay. And SSA introduces this somewhat mysterious phi function, which didn't exist in the original program. And what that is doing is that it's merging the different values of y that come along the 2 different paths. So along this path, the left-hand path, you get y2 entering this node. On this right-hand path, you get y0 entering this node. And so what the phi function does is that it just records this fact, okay? And says that the correct value of y, if you're coming from the left, is y2. If you're coming from the right, it's y0. And that correct value is given a new name, which is y3. And so now the print statement becomes print of p, which is the original parameter to the function, x0 and y3 instead of p, x, and y. Okay. So that's the SSA transform. It is a critical building block of most modern compilers. And the reason for that is that it actually, even though it doesn't optimize anything, it makes real optimization, subsequent optimizations, much easier to program. And so that's the benefit of keeping your program in SSA form. But how would you certify it? So you'd start by saying that everything is equal to begin with. Now on the left edge, you know that the value of x on the left is the same as x0 on the right, and the value of y is the same on the left is the same as y0 on the right. If you go one more step, you know that x and x0 are the same, and y and y2 are now the same. Now you do the same thing on the right-hand branch, and you know that x and x0 are the same, and y and y0 are the same. So this is just following, making more precise the informal explanation that I just gave. The same relation holds for edge E4. I haven't drawn it, it would clutter up the picture. And now at this point, something interesting happens. You know that the value of x is the same as x0, and the value of y is the same as y3 at this intermediate step. This is dotted because you don't actually express it as part of the witness. It's computed while you're checking the witness. And what this guarantees is that the print statements are going to produce exactly the same values on the left and right. Okay. And of course, at the end, you have this. Right, so I'll let you stare at this for a while. I'll see if there are questions. Okay. Yeah. I think the last question is about whether there's another process doing something with X. And yes, I'll come to concurrency. It is. All this is for sequential program transformation. Okay. So how would you create this proof? So now to create this proof, you have to know a little bit about the algorithm and how it works. So the algorithm is a really beautiful algorithm. It has two stages. The first stage is purely graph theory. What it does is that it identifies for each variable nodes that require these phi assignments, right? The merge assignments the merge points. So it basically identifies merge points, but not every merge point requires a phi assignment for every variable. You can be much more parsimonious about figuring out which nodes need the phi assignments, and that's the cleverness of this algorithm. So it applies, really interesting graph theory, the graph dominators calculations, to figure out that in the previous example, only node N2 needs a phi assignment, and it actually needs it only for Y, not for X. So that's the first phase. The second phase is that once you have this information, you walk over the graph and renumber all the assignments and all the uses of variables. Okay? And that uses an auxiliary stack that tracks the current name for each variable. So remember, the variables are getting fresh names as you walk through the graph. And so at different points in the graph, you have different names that exist for the variable. Okay? So that's how the algorithm works. And it turns out that this is exactly the part that we need to generate the proof. All we care about is, what's the current name for the variable. So let me illustrate this on this graph. So you're starting with X and Y just with an empty stack, and that tells you that everything is equal. Then at an intermediate step, you have renumbered X to X0. So that's what you keep track of. Y hasn't been numbered yet. You're just processed the first assignment here. Okay. Once you process the second one, you know that X is represented by X0, Y by Y0. Okay. Then that gives you the second edge. Then you process this one, and it tells you that Y is now represented by Y2. So the top of the stack is the first element of this list. That gives you this edge and this relationship. Okay. Now you follow the other edge. So at this point, X is represented by X0, Y with Y0. So that gives you that relation. Now you do the same thing for E4. And that also tells you to how to fill in the phi function. So you know that from this side, Y must be Y2. And on this side, Y must be Y0. Okay. So once you've filled in everything, you get to the last stage and generate the last horizontal link. So that's the way you construct this transformation or construct the witness. Okay. And now it turns out that I actually implemented these both with actually help from students, which I'll get to at the end. Certificate generation for LLVM transformation. So we did for loop unroll, for dead code elimination, and for mem to reg, which is the SSA transformation in LLVM. So the blue bar tells you, this was done a few years ago, the blue bar tells you the lines of code for that transformation itself. And then these are the additional lines of code that we needed to add. So the ones in red are the ones you actually add to the compiler that produces some raw information that gets converted into this logical representation of witness relations by some OCaml code. So you can see that it's not a lot of code. And in particular, it is very simple code. So even though this looks like it's half the code of the actual SSA transformation, most of what it is doing is just printing and rearranging, printing out useful information and then rearranging that information to be in logical form. Right? So it's really simple code. And together with Anton Shu, who was my summer intern last summer, we've been programming an actual self-certification system for WebAssembly, which is a different intermediate language. It's a stack-based language. It runs in all browsers. It's meant to, meant to make it possible for people to run C and C++ and Rust and JavaScript programs within the browser. So here we implemented these optimizations in OCaml, and we also implemented the corresponding proof generation code and the proof validator for WebAssembly. So you can see that for SSA, we needed about 700 lines of OCaml to program this transformation, and only about 130 lines to generate the proof. And very similar numbers for dead store elimination. The un-SSA transformation reverses SSA. That's necessary because fee functions don't really exist. So you have to remove them before you generate code for a processor. The compressed locals is something peculiar to WebAssembly, where you're basically defragmenting the local variable space. And now it might be suspicious that all of these are 500 lines of code. It's because there's a lot of similarity in the way these optimizations work. They all make passes over the graph. They all sort of adjust the instructions within each basic block. And so there's a lot of code that looks very similar, but does slightly different things. But what you can see is that the amount of effort for proof generation, the amount of work that I as a programmer or we as programmers had to put in is very small. And it again amounts to really keeping track of a few things and then producing the result. Okay. So I'll skip over the actual refinement checking method. It's just a work list algorithm that does simulation checking. Okay. And so, like I already explained, for the particular SSA transformation, what you have to do is to write an SMT formula that says these two edges are connected and everything is equal on those edges. This is the semantics of the target step. Here's the semantics of the source step. And I want to conclude that this relation holds. Okay. Now, I haven't shown you the fact that there is also memory, there is a stack of values, and you have to talk about how those are connected as well. But in this case, the memory and the stack are equal on both sides, right? So that's another equality, but it's an equality between arrays. So you really need uninterpreted functions, you need equality, and you need arrays in order to handle SSA. That's all you need. Okay. So in a few minutes that I'm left, let me talk about some practical challenges. So one is that refinement checking doesn't always require the most precise semantics. And so there are choices one can make that are perfectly okay. And choosing the right level of abstraction actually speeds up the checking. Right? So, and this tells you how big the checker for WebAssembly is. About half of that 4,000 lines is really graph manipulation code, which you still have to trust. And about half is the implementation of the proof checking. Right? And we use Z3 to share the queries. Now, the performance is bad. Refinement checking is slow. And this is not because there are the checks are themselves complex, but because there are so many of them. Right? So the LLVM validator would take an hour and a half to check about SSA for spin, about 20,000 lines of code. The WebAssembly validator takes roughly an hour to check SSA for the WebP image libraries, which is about 50,000 lines of C. Right? There are caveats. So the first one uses a very highly simplified LLVM semantics. The other one, doesn't exclude some functions from checking because they have floating point operations that we are not modeling in this bit level encoding. And some of the checks time out. And what we found was that if we reran those checks with a slightly higher time limit, then they would succeed. So it's really a matter of good engineering. So there's lots of room for that. Let me go a little bit beyond. I see a question on loop swapping, which I'll get to in a minute, and also a question on whether the proof validators have been formally proved. And I haven't proved our proof validators, but I would expect that they should not be that difficult to prove. It would basically amount to showing that they are generating the right simulation checks, the inductive simulation checks. So I'm hopeful, but I haven't actually done that. Okay. So this slide gets to the very last question on Slido, which is that there are optimizations, and also some earlier questions, which is that there are optimizations that are not easily checkable. And one of them is loop reordering. So because what you have to do is to match up unbounded reordering of actions. So you might have a loop that goes left to right, and then another loop that goes right to left. and they are supposed to produce the same result, but they don't. Rather, they have to produce the same result, but that cannot be checked step by step because the loop, the sequence of operations has been completely reordered from left to right to right to left, and that could be unbounded. So you have to do something else. You can, of course, write a simulation relation for this. It just turns out that the simulation relation is complex. It requires auxiliary arrays. It requires quantification, all of which is hard for SMT solvers. But the solution, and there exists one, is to use specialized proof rules. So in effect, for loop reordering, the proof rule would make sure that the reordering doesn't damage any dependencies that exist in the source program. And that check you can actually do with quantifier-free checking. And so I've implemented such a system for LLVM with one of my summer interns, Nimit Singhania, and that works really well. So somebody else asked a question about concurrency. Now, it is true that standard optimizations, if you apply, they are really correct for sequential programs. If you apply them to concurrent programs like this one over here, where the flow, it's concurrent, it's two threads in different functions, but they are connected through these receive and send statements. So the flow of execution is like this. And so you get x equals 1 and y equals 1 in the end. But the compiler, if it separately optimizes each one, would think that variable x is unused, so this can be removed, and variable y is unused in this block of code, so it can be removed. And so you would get this program which would print x equals 0 and y equals 0. So trying to figure out which optimizations are so-called thread safe, and how to generate, what kind of certificate to generate for this is very much an open problem. The other big area that people are working on, many people have worked on, and it's a very active area, is secure compilation. So it turns out that compiler optimizations could introduce security holes. So you could read a password, use it, and then clear the memory that you stored for the password. This is a good thing to do. But to a compiler, this assignment looks like a useless assignment because it's the value of x is never used in the rest of the program. So it just can remove it. GCC does this, LLVM does this, you can try it out. And what that does is that your password is now leaking through the rest of the program, right? And might be picked up by an attack that actually happens somewhere else in the program. So trying to protect against this and trying to certify compilations as being secure is very much an open question. So let me sum up and say, going back to what Dijkstra was saying, that you should actually design your programs with the correctness proof in mind. Now that is an ideal that we should go for, but it's not something that current tools are capable of supporting. So I think of self-certification as being in that flavor of program development. You're asking the programmer to do something more. You're asking them to write a witness generator and use a checker at the end. So you're kind of building verifiability into software, and that's a good thing to do. And as you've seen, a complex compiler can be verified using a small and trusted validator, and that's actually a good thing too. And the design of certificates is definitely an art. There's not one algorithm that works all the time, but you can see that it's guided by deductive proof principles of refinement checking, of inductive invariance, and all of which we are very familiar with. So this is really something that the CAV community can take up on. So let me just say thanks to a number of people, in particular, a bunch of really talented summer interns who I've had the pleasure of working with. And thank you to DARPA and the NSF for supporting the research, and you for listening to this talk. So let me go to some questions. Yeah, I think.
Yeah, there were like two questions, so pending.
Right.
One is, what is the semantics of WebAssembly that you use?
Yeah, so we are building on top of the WebAssembly reference implementation. So there is an OCaml program that is a reference interpreter for WebAssembly. We are building on top of that. Now, for our checking, we haven't implemented yet the complete, like full detailed semantics of WebAssembly. So we've implemented a slightly simplified form where we are allowing integer operations. And for loads and stores, we assume that the loads and stores are aligned in memory. Now, the full semantics allows unaligned operations. It also allows floating point operations within the code that we currently don't handle, but we don't see a big issue with handling them in SMT. It's just a question of more engineering and slightly some more amount of implementation.
And then there was one about what about optimizations that desynchronize the two programs, like for instance, remove skip.
Yes. So there you have to right. So that's a good question, and that comes down to what you mean by a step of the source or target programs. So in fact, in our validator and in our proof generator, we allow a step to be an entire sequence of basic blocks. So it's not a single instruction at a time. It's actually a sequence of a loop-free sequence of basic blocks. And what that does is it lets us handle optimizations where, for instance, you have a pair of basic blocks that get squished into one basic block. Right? So there is a certain amount of stuttering or desynchronization that happens. And it turns out that this idea of looking at, control flow graph paths instead of single instructions suffices to handle the kinds of optimizations that we have come across. And there are, more complex proof principles that one can use if that doesn't suffice, but we haven't actually had a need to use those principles.
So we'll take one last question. So did writing the witness generator led to detecting bugs even before you ever check a certificate?
Yes, that's a really good question. And yes, so I implemented some of these witness generators so I can talk from personal experience. It's a lot of fun to think about what the witness should be for a compiler optimization because you don't find these in textbooks. Textbooks just tell you what the optimization does. It doesn't tell you why it's correct. So you have to sort of reverse engineer the correctness proof. And it also, it doesn't help me detect bugs. I haven't found a bug in a published optimization. I've found bugs in my own code, right? So I sort of, write. So when I was writing the SSA transformation for WebAssembly, and I of course made a few cut and paste mistakes that the kind that everybody does. And it turned out that for the first few programs that I tested, the checker actually detected the mistake. So I was expecting the programs to be equivalent, but the checker said they weren't. And so when I went back and kind of tried to figure out where the problem was coming from, I realized that I had made this cut and paste mistake. So I think the attempt to get to more to the point of the question, I think trying to write out a proof of correctness or think about the proof of correctness actually helps you do a better job of writing the transformation itself. And of course, you have this nice safety net that even while you're being careful, if you make some silly mistake, the checker is going to catch it for you.
Okay, thank you, Kedar, for the very nice talk. So I guess we will